Hi, it's Dr. Kahn with Chapter 3, Section 3.3 and 3.4. In these sections, we'll be talking about sedimentary rock and metamorphic rock. Section 3.3 talks about sedimentary rocks. They form from sediment or weathered material that's either solid or in solution. About 75% of all rocks that we can see at the surface on the continents are sedimentary rocks, and they're very important as they hold clues to what past environments looked like, felt like, and information about the sediment that gets transported and how it gets transported. And sedimentary rocks also play an important part in telling the evolutionary history of our planet because they contain fossils that help us learn about how life evolved on Earth. The first type of sedimentary rock is detrital sedimentary rock. This rock forms from solid particles that broke apart from weathered rocks. They're classified by particle size and shape. Common examples include pebble-sized particles all the way to boulder-sized particles that are put together or lithified into rock. Conglomerate is one example. This example has larger particles but rounded or well-rounded sediment. Breccia also has large-sized pebbles or boulders, but the sediment that it includes is angular in nature, meaning it just has sharp edges. Medium-sized particles include sand, and the sand sediment forms into rock called sandstone. The smallest particles are the silt and clay particles that form rocks like siltstone and shale. Figure 3.16 in your book indicates the different types of detrital rocks and gives you an example of each and what it looks like. Here again, we see conglomerate with its rounded, larger pieces, while breccia has large pieces that are angular. Sandstone, we can see the grains of sand somewhat within the layers here. Oftentimes we do see a layering or bedding. And finally, the smallest pieces being so small we can't necessarily make out individual particles. These will be our shales, mudstones, and siltstones. Other types of rocks include chemical, biochemical, and organic rocks. Chemical, biochemical, and organic rocks form from dissolved ions that are carried in solution. They're carried through water into lakes and to oceans as well. From these dissolved ions, solids can precipitate or come into a solid form in the water. This would be an example of a chemical sedimentary rock. Or sometimes the water evaporates, leaving behind whatever was dissolved in the water and laying down sediment, which is also a chemical process. Or if it's formed from something that was once living, it's considered an organic sedimentary rock. Or if it was made by something that was once living, like a shell, to a sea creature, for example, it would be a biochemical. These rocks are classified by composition. Calcite, which is calcium carbonate, can form through chemical precipitation. In other words, it's coming out of dissolved ions into solids within the ocean and making the sediment that forms limestone. Calcite can also be the mineral that forms from biochemical processes, like limestone that's made from a lot of carbonate shells from small ocean organisms, laid down over a very long period of time and compressed into a stone. Another composition of our chemical rocks include quartz, mineral coming out of the ocean. So it's quartz that's dissolved in an ionic form in the ocean, and that quartz is then precipitated into the material chert. The next category are the evaporites. Gypsum and halite are examples of minerals that can get left behind when we have a lake, for example, that dries out, and it leaves behind whatever ions were dissolved in the lake. And finally, organic matter, altered plant materials that were left and laid down and compressed over time. The example is coal, which actually formed from kind of a swampy environment with a bunch of trees and other plant type material that was compressed into a rock. Figure 3.17 indicates common chemical, biochemical, and organic sedimentary rocks. The process of forming a rock from sediment is called lithification. It has two steps. First, the particles that make up the rock are compacted through pressure. They're sitting closer to each other than previously, so they're compacted into a smaller shape. Their volume decreases, and then a process called cementation occurs. This is where usually a fluid that circulates between the individual particles leaves behind calcite or silica or something like iron oxide that serves as the glue that holds these particles together. So they're literally cemented together in place with either calcium carbonate, silica, or iron oxide. Sedimentary rocks often include strata or bedding. These are accumulated layers of sediment that were laid down at the same time and have similar characteristics. These are almost like pages in the book where past events and past environments are recorded in the sediment that's laid down, and geologists can use these layers in order to interpret what the environment was like. Fossils are defined as trace remains of prehistoric life. They're incredibly important in sedimentary rocks. They help us correlate layers of rocks so we can see how one area's rocks are related to another area's rocks. And they're also used to match rocks of different places over different times. Sometimes sedimentary rocks can even include things like ripples in shallow lakes or oceans. Section 3.4 talks about metamorphic rock, which is a pre-existing rock that changes in some way because its environment is different from how it formed, or the place it formed, or the conditions under which it formed. It's important to note here that although temperature and pressure play a key role in transforming one rock to another type of rock, the rock cannot melt. If the rock does melt under high temperatures and pressures, it actually will cool to become an igneous rock, not a metamorphic rock. So high temperatures and pressures do play a role in altering the conditions and altering the mineral arrangements of a metamorphic rock, but as soon as it melts, it becomes igneous. Changes that we see in metamorphic rocks include changes to the minerals themselves, so the atoms are rearranged, or maybe just a change in texture, so something goes from a fine-grained texture to recrystallizing into larger crystals, and chemical composition, sometimes with an introduction of water that's carrying new ions or new materials to form new types of minerals. But again, it does not melt through this process. Metamorphic change happens slowly over time. There are different degrees of metamorphism. With kind of lower temperatures and pressures, we get what's called low-grade metamorphism. An example here, shale is our sedimentary rock, but it turns into slate under low temperature and pressure regimes. High temperature metamorphism, these are significant changes due to very high temperatures and pressure regimes. The original features of the rock are almost erased. You might not be able to, for example, see the layering of sandstone as the crystals are recrystallizing into larger quartz minerals. Another example, so shale from our low-grade metamorphism, once we apply more temperature and pressure, can become the metamorphic rock called gneiss. That's this one here. It's pronounced nice. So metamorphic grade refers to the extent to which a rock has changed or metamorphosed. And here again, our parent rock is shale. This is a sedimentary rock, but with some heat and pressure, we can change it to slate. And we see that these clay minerals are now more aligned. Slate is used and cleaved off in these sheets for things like roofing, roof tiles. And here we have a parent rock that's like granite or diorite. Here we have randomly oriented minerals, but under a lot of heat and pressure and compressional forces, the crystals will actually rearrange themselves into layers and form these bands or foliations. Metamorphism is driven by heat and pressure. There are two types of pressure that the book talks about: a confining pressure and then differential stress. Confining pressure is from all sides and will work to reduce the volume of the rock, so it pushes it really hard. Think about squeezing a marshmallow from all sides. Differential stress occurs from mountain building events related to plate tectonics, and we might have stress that is greater in one direction than another direction. And the third agent of metamorphic processes is chemically active fluids. This is water with dissolved ions that's leaking or inside the rock and forces minerals to recrystallize using this new material to form minerals that weren't there before. Smart Figure 3.28 talks more about the difference between confining pressure and differential stress. Again, our confining pressure pushes from all sides and just makes things smaller, where our differential stress will actually work to give us this foliation due to mountain building events. We see here that the crust is coming together. We have some kind of convergence forcing these mountains upward. And as a result, we actually get a bending of the rock, or this foliation, in response to that heat and pressure. So foliation talks about this flat or layered arrangement of minerals or grains. And we can actually see which way the compressional force is occurring because minerals form perpendicular to that compressional force. We can see foliation in rocks like slate, all the way up through with increasing metamorphism to our highest grade metamorphic rock, gneiss. Not all metamorphic rocks are foliated or have lines. Some non-foliated textures can occur when the same size crystals regrow. In other words, we grow larger crystals that are all about the same size as each other. So for example, if we have sandstone, it starts off with small parts of sandstone, little pieces of sand that are lithified together, but under heat and pressure, these quartz crystals will regrow into a larger network of very coarse-grained crystals, and we call that quartzite. When limestone is the parent rock, the recrystallization of that calcium carbonate or that calcite mineral forms large blocky crystals we call marble. The rock is called marble. Smart Figure 3.2 shows an example of a confining pressure and then metamorphism after differential stress. So before, we have kind of a random arrangement of these minerals, and then after, we see that these minerals have kind of formed together in bands or lines according to the type of mineral. This figure 3.30 indicates the common types of metamorphic rocks that you might see in your lab kit. And that concludes 3.3 and 3.4. Thanks for listening.